Hello, AP Chem. This is our last official lecture of a unit before the exam. It's over pH and solubility. We did a little bit of introduction to acid-base reactions, if you remember, at the end of Unit 4. This week, I'm going to try to go over, do a lecture on titrations a little bit, because that is a popular experiment to display on the AP exam. If you remember, that's one of the ones that they do where they ask you to read the burette, to do a sig fig measurement and things like that. So I will try to do a little review on titration, since we never really got to do a titration experiment in class because COVID happened. But yes, we will be talking about pH and solubility, and how it affects basically the solubility of salts and equilibrium. So one thing to think about is the autoionization of water, which is like self-ionization. So when water forms ions with itself. So you can kind of think that water itself sitting in a glass kind of experiences this dynamic change. It doesn't necessarily just stay as water molecules. The pH overall is equal, neutral, 7 to 7, because the H plus, often showed as H3O plus, and OH minus kind of balance each other out. So it's not that water becomes acidic and basic and goes back and forth. It's all balanced in the end. So in pure water at 25 degrees Celsius, the concentration of H3O plus hydronium ions is equal to 1 times 10 to the negative 7. And the concentration of hydroxide ions is also equal to 1 times 10 to the negative 7. So they kind of balance each other out. So since the concentration of H3O plus is equal to the concentration of OH minus, the solution is neutral. We'll talk a little bit more about the pH scale in a few slides. So if we make a constant for the autoionization of water, Kw, it's equal to the concentration of hydronium ions times the concentration of OH minus hydroxide ions. We do not include liquid water in the equilibrium expression because it's liquid. We only include aqueous or gaseous things in the equilibrium expression. So if we actually calculate the Kw of water, it would be 1 times 10 to the negative 7 times 1 times 10 to the negative 7, which is equal to 1 times 10 to the negative 14, and that's true for water at 25 degrees Celsius. So this, of course, is a constant. It doesn't change. If we know the concentration of H3O plus, we can calculate the concentration of OH minus because it should be equal to Kw as long as the temperature stays at 25 degrees Celsius. It is a very useful constant, so it is helpful to memorize it rather than to have to look it up every time. I do not believe it's given on the equation sheet in the exam, but this exam is an open note exam, so you do have the internet to use and everything. As long as you're not copying and pasting from websites, you have the internet to use as a resource. However, on usual AP exams, it would be a constant that we recommend you memorize because it is extremely useful. So, since Kw is a constant, if we were to increase the concentration of H3O plus, then the concentration of OH minus would have to decrease in order to balance out, because to equal the constant, if you raise one variable, the other one would lower in order to balance that out. So the pH of a solution increases as the concentration of hydronium ions decreases. So remember, a low pH means acidic, and a high pH means basic, and 7 is neutral. OH minus, if there's a higher concentration, the solution is considered basic. If it's a lower concentration, it's considered acidic. And then with acidic hydronium ions, more would be acidic, less would be basic. So again, with Kw, if you were to increase or decrease one of these variables, the other one should have an opposite change in order to keep that constant a constant. And if you change the temperature, that constant is going to change. So if the temperature isn't 25 degrees Celsius, it would be equal to something other than 1 times 10 to the negative 14. But if it's at 25, it's going to be 1 times 10 to the negative 14. And regardless of the temperature, these two concentrations should have an inverse relationship with each other. Some cations can acidify solutions, so that would be to lower the pH of a solution. And so ionic compounds containing NH4+, for example, can acidify solutions. So NH4+ is the conjugate acid of NH3. If you remember from strong acids, strong bases memorization, NH3 is a weak base, so the conjugate acid is therefore a stronger acid, NH4. So if we add to water NH4NO3, we would see NH4 react with water to donate, act as a proton donor to create NH3O+. Okay, so NH4+ is acting as an acid. It donates its proton to water to form the hydronium ion. So the pH drops below 7 because the concentration of H3O+ increases. We also have monoatomic cations that can release protons from H2O. So monoatomic meaning one atom. So from the periodic table, if we have an ion, specifically a cation, it can release protons from H2O. So cations attract the negative poles of H2O because they're positive. So if you remember like the Mickey Mouse shape of H2O, Mickey Mouse's chin is kind of where the negative part of the H2O molecule lies. So the cations, which are positive, are attracted to that Mickey Mouse chin. The positive charged cation then decreases the electron density to the OH bonds. Okay, so electrons, there are electrons in those bonds. When we have a positive cation coming to the party, those electrons are kind of distracted and they're looking towards that cation, which then weakens these bonds. That weak bond allows an H+ ion to break free, therefore creating an acidic solution. So for example, if we have iron 3 chloride added to water, iron 3 chloride attracts that OH part of, well, really the oxygen part of the molecule, but the water usually just releases one hydrogen atom, which is there, which increases the acidity of the solution, lowering the pH below 7. So H+, the hydrogen ion, and hydronium, which is H3O+, scientists kind of show them two ways because often this H+ will find another water molecule and form H3O+. So that's kind of why you will see both. So the ability to release that proton from water, so to attract that OH from water and then release an extra H, will increase as the ionic radius decreases. So remember, as the ionic radius decreases, there's a higher effective nuclear charge between that cation and the electrons that are in the water molecule. And then as charge increases, of course, that would also increase the effective nuclear charge felt by those electrons, pulling them so that an H+ can release. So the larger the attractive forces, the greater the decrease in electron density between the oxygen and hydrogen in the water molecule. The conjugate acids of strong bases don't have the ability to hold onto OH ions in water, so they don't really, they're not able to attract H2O. So strong bases, if you think about it, if you put a strong base in water, it dissociates completely because it's a strong base, a strong electrolyte. Because it's releases from that, it's not really going to want to grab onto an OH molecule. So conjugate acids of strong bases will not have this effect on pH. Okay. There are also some anions that make a solution basic. So anions that are conjugate bases of weak acids accept protons from water to produce OH-. So remember, a weak acid, its conjugate base is going to be relatively strong. Remember, those have an opposite relationship. So a relatively strong base is going to be a proton acceptor. It's going to accept a proton, but an OH- is going to be left behind, which then raises the pH, making the solution more basic. The conjugate bases of strong acids will not raise the pH of the solution. So conjugate bases of strong acids are going to be weak bases. Okay, you can think about it that way. You can also think strong acids, like HCl, for example, that's a strong acid. They dissociate completely in water. So it's very unlikely that the Cl minus ion is going to take that H back to become that HCl because it has a strong dissociation in water. So you can kind of think about it that way. So if we think about NaCH3CO2 being added to water, it dissociates 100% because it's a soluble compound with sodium. The CH3COO minus is going to interact with water. It will steal basically one of the H plus, the hydrogens, leaving OH minus behind in the solution. Because OH minus is left behind, the concentration increases, which makes the solution more basic. Sulfate ion is a very weak base. Okay, so HSO4 minus is fairly strong acid, so the Ka value for that is 1.2 times 10 to the negative 2. That's relatively high, so it's a pretty strong acid, and strong acids have a weak conjugate base. So SO42 minus, its conjugate base, is relatively weak. So if we have sodium sulfate, it's going to dissociate into 2 Na plus and SO42 minus. SO42 minus will accept a few H plus, and it will result in a small change in pH by taking away those H plus ions. The carbonate ion, which is CO32 minus, is a stronger base than SO42 minus. So carbonate ions tend to raise the pH of the solution more than sulfate ions for the same reason that they take H plus molecule, or not molecules, H plus ions out of the solution, which raises the pH, making it more basic, but they're more effective at doing it than sulfate is. We also have metal oxides that can act as a base. So metal oxide is any metal cation that's bonded with oxygen. That's what the oxide comes from. So it's an ionic compound with a metal and oxygen. So what happens, if we have MgO solid, it might slightly dissociate into Mg2 plus and O2 minus. And the O2 minus can then react with water to create 2 OH minus hydroxide ions. So if we kind of put these two equations together, we get magnesium oxide and water reacting to form Mg2 plus and 2 OH minus. So since this is relatively insoluble, if you look at like the solubility constant for magnesium hydroxide, it's relatively low. So magnesium hydroxide will form a solid. However, even something that's considered insoluble does dissociate a small amount when in water, when in a solution. So it's not that its dissociation is completely zero, it's just very, very low. So even the slightest solubility of solid hydroxide will increase the concentration of OH minus in a solution, making it more basic. Okay. So here's an example. We want to write the net ionic equation for reactions that take place when solid potassium oxide is dropped in water. Okay, so the first thing I want to write is going to be that reaction between potassium oxide splitting up into its ions. So potassium oxide, to balance charges, K has a +1, O has a -2. We crisscross to make our potassium oxide formula. It's going to dissociate into O2 minus and 2K plus. Remember that O2 minus reacts with water to make 2 hydroxide ions. If we write out the net equation just simply by adding these two things together, you will notice that the O2 minuses will cancel out. So you're left with K2O solid plus H2O liquid, yielding 2K plus and 2 OH minus. So it does not form an insoluble compound, remember, because K plus is from group 1.